my teaching method. So I like to keep everything pretty open. Don't be worried about interrupting by speaking up. The questions help everyone. And if you want to, you can just ask the questions in chat. I don't see them right away. I'm not ignoring you. I do look at them periodically, and I'll always get back to them. So if you have any questions, just speak up on the microphone or ask in chat. So let's go ahead and get started with microservices and talk about what we're going to be learning. So we're going to go over what is microservice and what a monolithic architecture is. And we're going to talk about the challenges with the monolithic architecture, the monolithic development lifecycle, the drawbacks of a monolithic architecture, what a microservice is, as well as the benefits that microservices give us. We'll be going into how we actually use microservices and the anatomy of a microservice and how we can actually build microservices. We'll also be getting into the ecosystem of microservices, service meshes, principles of microservices, and the challenges of microservices. So there's actually going to be quite a lot of talk about microservices today. And then once we're done with microservices today, it's going to set us up for learning containers, which is what Docker is all about. And then in the next section of our course, we're going to talk about Kubernetes, which is a way to have our containers running on lots and lots of different servers. I see a question in the chat from Kobe, and he's asking how many sessions do we have with Brad? So I believe it's going to be 12 to 13 classes. We have this class on microservices, which is very heavy in the lecture components. But then we're going to do 5 to 6 classes on Docker and containerization. And that's going to be some theory as well as a lot of hands-on labs. And then we're going to get 6 classes of Kubernetes and deploying our containers and our applications to Kubernetes cluster. So it's around 12 to 13 classes. So I'm just going to go to presenter view here and get everything a little more in. So let's talk about microservices. But before we do that, we need to know about the monolith. So monoliths are known as, this is a monolithic type of application. And these types of applications can be good when you're starting out. Basically, it just means you build the entire application basically into a single binary. All the code is sort of put together in a single repository. You build it out, you get a single artifact, and you deploy that. All your different services are part of this monolith, this big piece, this big giant piece of code, right? So they're pretty good when you're starting out, but you run into a lot of problems, and that's what we're going to get into. So let's talk about the monolithic architecture. So with the monolithic architecture, all components are deployed in a single unit. So we sort of have an example application here, and you can see, you can kind of guess what this application would be about, right? It's for booking flights. And within, just think about when you've booked a flight. So you had to go onto the airline, you had to sign in, you had to find a flight, you had to book it, you had to assign seating, you had to make a payment at some point. There was a lot of different things that made up that experience for the user, right? In a monolithic application, all those different components are built into the same code base. So this can present quite a few problems that we're going to be going over. But just have a look at this here and just think of it, your monolithic application being all the components of your application together. So since everything is together, we need to deploy the entire code base if any change is made to any of these components. If we were to make changes to the payment system or the payment code or anything to do with payments, the entire code base would have to be redeployed, right? If you made changes to booking, you would have to redeploy the entire code base. So any change you make to a monolithic application requires a redeployment. Also, you're kind of constrained with the technical stack that you use. You can see here, our application has many different components. If we built this application in Java, then we would be stuck building every different component of this application in Java, right? Whereas we don't really like to be constrained with our actual tech stack. Sometimes we like to build services using Python, right? You can't really mix and match with a monolithic application. And it goes more than just like your actual programming language, like Java versus Python. It goes down into the individual libraries and operating system requirements, all the different environment requirements that your application requires. All these different components need to conform to those requirements, right? So they'll all need to run on the same type of operating system. They'll all need to use the same Java libraries. Everything needs to be the same in a monolithic architecture because everything is sharing the same system. Also, you run into problems when you grow larger teams. You have to be careful that you're not messing up anyone's code. All these different components of the code become very tightly coupled. And if you make a change to the booking system, it might cause problems downstream to the flights system, the customer system, or the payment system. So when you're working with a monolithic architecture, you run into those problems a lot more frequently. And then finally, I sort of mentioned it at the start, but anytime you make a change to anything in this code base, it doesn't matter how small the actual change is, you're going to have to redeploy the entire application. So we sort of mentioned what the drawbacks of the complexity were there. So I'm going to go over them just in a little bit more detail here. So here are the different drawbacks. You have complexity, and this is the complexity for a monolithic architecture is more about when you're actually implementing the changes. Monolithic architectures are somewhat simpler than a microservice architecture because you're basically working with a single code base and you can just look in that code base and find everything that you need. However, you need to be very careful when you actually make changes, right? Whereas when we look at a microservice architecture, the code bases become much smaller. So the code bases are a lot easier to work with in a microservice architecture, but microservices do come with their own complexities that I'll get into. But both of them have some type of complexity with them. And usually with monolithic type applications, that's because they're tightly coupled. And that just means that the different components of the application become dependent on each other when they really shouldn't be. Also, scalability becomes a huge issue with a monolithic application. If we look back at our example, and if any of these services needed to be scaled up because the booking part of the application required more users to use it, whereas not every single user gets to the payment portion, you can't scale up the individual components. Also, it becomes very hard to scale up the database. Just basically any type of scaling that you want to do with a monolithic application becomes almost impossible once you get to a certain threshold. Whereas a microservice architecture, you can scale up individual components of the application quite easily. Also, what if one service in the application needs a different version or library? So we sort of discussed that earlier here. With a monolithic application, you're stuck with a certain tech stack and certain libraries. And then finally, the release process is longer, and basically that comes down to whenever you make a change, you have to release the entire code base. And because you're releasing the entire code base, your CI/CD pipelines are going to take a lot longer to run. You're going to have to run through your entire test suites every time. So the release process becomes quite long with a monolithic application. So just more summarized reasons of the problems with monolithic applications. So difficult to scale. The architecture for monolithic applications is very hard to maintain and evolve, and this gives us a lack of agility. Agility meaning like the ability to move forward quickly, right? It's very hard to make changes to monolithic applications. They take a long time. You have very little agility and very little velocity. This also causes long build times and release times. We sort of went over that. Basically, every time you make a change on your monolithic application, it's got to rebuild the entire code base. It's got to run every single check. So this takes a long time as well. And then finally, maintaining a monolithic application becomes quite difficult. Basically, any change that goes out could affect the entire application, right? Things aren't compartmentalized into smaller components. Any change that goes into the code base, the operations team sort of needs to be aware of how it could affect the entire stack. So just a quick look at a basic pipeline here. So you have lots of different developers working on the monolithic application. And every time they commit a code change, it's going to have to build, test, and release. And basically all the different changes come together sort of like little pieces of Lego. Let's get into microservices. And I think talking about microservices are going to make you understand monolithic applications quite a bit more, and the benefits that microservices give you, that it's really going to help your understanding. So what is a microservice? Well, a microservice is basically taking an application and then splitting it all into different services and different code bases. So we can see it's our same flight booking application, but instead of everything being in the same code base and a single binary, we have all these different little microservices. So you can see we have a microservices for the flight booking, the flight management, the seat reservation, check-in. All these different components are managed separately as microservices. So when we're talking about microservices, we need to think about quite a few different things. How do we actually break down the application into microservices, also known as decomposing? We'll get into that towards the end of the class. We'll also talk about where the code goes and how many services you should actually create. When you take your monolithic application, how do you decide how many different microservices it should be broken down into? You should also decide how big or how small these services will be. And finally, how do these different components actually communicate with each other, right? That is a big component when it comes to microservices, is the actual communication between the services, because and that's sort of one of the complexities that comes with microservices, right? We're simplifying our actual code base for each of these services, but we're adding more complexity on how the services talk to each other, right? With a monolithic application, everything's basically just stuffed into the same server, and it's much easier to have the communication work on the same server running the single binary than it is to have all these different servers running all these different microservices, and they're all talking to each other, right? So that's where the complexity comes in with microservices. So a microservice, we want to decompose our monolithic application into smaller components known as microservices. And usually this is done based on business logic or the business unit. The best way to understand it is sort of the business logic or the application logic, right? We know the customer management system, CRM, is different than the actual like flight booking stuff. There's not a lot of components that work together with these things, so we can break them down into different components quite easily. And now we have two separate services that aren't tightly coupled, and we can maintain and administrate them separately. Now, microservices can communicate in a lot of different ways, but the primary way that you're going to see microservices communicating is through API requests. And sort of the secondary method that we use is known as message queues. So we'll get into message queues a little bit later, but let's talk about APIs. So an API is an application programming interface, and basically it's just how computers or systems can talk to each other, right? So nowadays, when developers are building backend code, they're building what's known as like a RESTful API server. And basically how a RESTful API server works is you send HTTP traffic to it. So that's just web traffic. You send a request to a certain API endpoint, right? An endpoint is just a portion of the URL. And basically, the backend service is going to give a response based on the endpoint that you sent the message to, right? So the different microservices talk to each other through HTTP using API endpoints. And this can go a little bit further when you start implementing what's known as service meshes. And you'll see this a lot in Kubernetes. And basically a service mesh takes control of the actual communication layer. So your actual applications don't need communication logic built into them. They're just serving requests, and the service mesh is controlling how the requests get to them. Let's talk about this because I think this will help a little bit. So this is an example of our application broken down into 4 different microservices, right? We have the flight booking, the flight management, the check-in, and the payment. And you can see that we have 4 different teams. So usually what you're going to see is you're going to see a single microservice for a single team. So a team is going to be responsible for a single microservice. And this gives us a lot of benefits, right? This team responsible for the flight booking microservice becomes an expert on all the functionality of the flight booking service, while the flight management team becomes an expert in that domain, and then the payment team becomes an expert in the payment domain, right? And these teams are no longer limited by each other, right? They can use whatever programming language they want, right? So flight booking can use Python, the check-in team can use Node.js, payment can use Go, and flight management can use Java, right? They're not limited to what the other team's using. They're all basically creating their own RESTful APIs for the microservice. And since the microservices are talking to each other through the API, it doesn't matter which code base they're using. Not only does it not matter which programming language or code base they're using, all the little dependencies of the libraries no longer matter, right? The Python team can use whatever versions of the Python ecosystem they want. They can use whatever version of Python they want, right? And it doesn't matter. They're not limited by the other teams. So I'm going to hit back onto a few more of these points here on the benefits that smaller teams gives us, but I think this is pretty good for now. Let's go ahead and move forward. And let's talk a little bit about the disadvantages of microservices before we continue. And the first one I have here is service interaction can be complex, right? So we're giving up the complexity of the actual code base for our smaller microservices, but we're adding in complexity of how the actual services like talk to each other and communicate to each other, right? You can see here this microservice architecture. All these different services can talk to different components, and it can get pretty complex, not only just for knowing how they talk to each other, but for monitoring these type of applications, right? Monitoring a single monolithic application is quite easy. You just go onto whatever server the monolithic application is installed on, you install some sort of monitoring software, and you're done. Whereas microservice type deployments and microservice type architectures, it becomes a lot more complex to get monitoring right. You got to use a lot of different observability tools to discover these microservices, to capture their logs, and to graph out their metrics onto dashboards and everything. Also, there is some extra communication logic with microservices. So basically, a lot of the code is you have to, if you worked with Python, you probably are used to creating a function in the code, right? And within your Python application, it's very easy to call that function, right? You just define the function at the top of your code, right? And then at some point within your code's logic, you call that function. So it's quite simple to do in a monolithic application, but in a microservice type architecture, you have to define how you talk to the payment system or how you talk to the check-in system, all that different logic, right? You have to wrap everything up into RESTful APIs and start using things like message queues. So the extra overhead of programming communication logic can be a little bit difficult. And then finally, ops teams have a lot of work to implement proper monitoring and observability, right? So lots of different services distributed across hundreds of servers, takes a lot of work to solution out an observability platform. Luckily, we have lots of tools to tackle these challenges, right? So some of the challenges that I mentioned is communication, containerization, or sorry, the tools that we use to solve these problems is communication. We use RabbitMQ is an example for that. It's a message queue type system. And basically a message queue is a way to get a message from one system and distribute it to a lot of different systems. I have some diagrams coming up that will explain that, but there's a lot of different tools that we can use for communication, like RabbitMQ. There's a lot of different ones out there. Containerization. Since we're going to break down our monolithic application into many, many, many different services, that would create a lot of overhead if we had to deploy each service to a physical server or a virtual machine, right? Virtual machines and physical servers use a lot of memory, a lot of RAM, and they cost a lot. Whereas if we use something like containerization, we can get really small services running on these little containers that don't take a lot of CPU, don't take a lot of memory. They have no overhead from the kernel. So we can have really small services running in containers, and tools like Docker help us solve that. Then we run into the problem of how do we distribute these microservices across more than one server, right? It might be easy to get lots of different services running on a single server, but when you're trying to get them running across hundreds or thousands of servers, you need something like Kubernetes, an orchestration tool. And what an orchestration tool does is it basically looks at all your services, all your containers, and then just chooses how many servers you need and deploys your containers to those servers as you need them, right? And you can scale up your application and scale them down. You can bring new servers online and then fill them up with containers. So there's a lot of cool stuff that we can do with Kubernetes. And Docker and Kubernetes is what we're going to be working on in for the next 12 or so classes. So that's exciting, because that's where all the fun happens, actually. But before we get to that, let's continue with the microservice stuff. And there's two more points that I want to talk about here, and that's service mesh and monitoring. So actually, Kubernetes does provide different types of service meshes, and service meshes just allow communications between your microservices, and it eliminates some of the complexity, so you don't have to program all the logic out. You just build up a service mesh, define a few parameters, and everything is sort of solved for you. And we can actually implement that with Kubernetes, and we'll have a look at how we can do that as well. But before we move to the next slide, let's talk about monitoring. And lots of different monitoring tools out there. We have Datadog, we have Prometheus, we got Grafana. Let's talk about Prometheus and Grafana here, which we have little pictures of them. So Prometheus is a way of exposing metrics on your servers or your microservices, and it also can extract those metrics quite easily. So we could have hundreds or thousands of containers running our microservices, and a Prometheus server can discover the metrics, scrape them all from our microservices, and then store them in a database. And then we can use something like Grafana to actually visualize those different metrics and view them into dashboards. And then we can start creating alerts, right? We can create alerts for when, if a microservice is using too much CPU, or, isn't responding to a queue. If a message queue is building up, you can make metrics. You can measure basically anything. You can measure latency, how long it takes a user to log on. Basically anything you could think of, you can measure, and you can graph out with a tool like Grafana. So lots of different tools that we can solve all the problems that microservices bring on. So we talked about some of the disadvantages. Let's talk about the actual advantages. Why we're putting in all this work to get microservices to work, right? There has to be some advantages, and these here are the 5 main advantages, in my opinion. So scalability. So microservices can be individually scaled up. I think I mentioned it a little bit earlier. Your when you're searching for a flight, that service might use a lot more processing power. There's a lot more users searching for flights than there are people actually making payments and finalizing payments for their flights, right? So we can scale up individual microservices quite easily. And if we're using tools like Docker and Kubernetes, it becomes pretty trivial to actually scale up a containerized microservice. You basically just change a single parameter. You could change the amount of replicas you have of a microservice, and changing that single parameter, you could go from 10 to 1,000, right? And we also have tools that will automatically scale our microservices up based on how much CPU they're using, right? So scalability of our actual services is something that microservices implements, and it also allows us to scale up our teams. And I'll get into a little bit of that in the next few slides, but basically, with a monolithic application, you run into issues with how many developers can actually work on the code base at one time, right? You can't just keep throwing developers and expecting each developer you add to increase how fast you can develop, right? 2 developers working on a single application goes, so fast. And if you add 2 more, it doesn't mean it's going to go twice as fast, right? It might not even go 30% as fast, right? You get really big diminishing returns as you add more developers onto a single code base. So microservices allow us to have smaller teams, and having smaller teams allows us to scale up how fast we can actually deploy our application and iterate on it. Flexibility. So flexibility, we sort of discussed that a little bit, but basically you're not locked on to single languages or single libraries. Basically, you can use whatever code programming language or libraries you want that your team's using, and team A will not affect team B, right? Team B can be using whatever different languages or libraries they want to use. So it gives us lots of flexibility there. We also get resilience. So if a single microservice failed, then likely it's not going to affect the entire system. Now, that isn't entirely true, because sometimes you have a microservice that lots of different microservices become dependent on. That's something you want to avoid, but these things sort of get built in everywhere in any type of complex application. But the key point is microservices usually prevent what's known as a single point of failure. Next is faster development. So since the application is broken down into smaller, more manageable components, this allows developers to rapidly implement new changes, right? So smaller components, a developer can make a change, and that change will get deployed a lot quicker. And then finally, my favorite advantage is these are complex systems, so these companies need a lot more DevOps engineers, right? A lot of engineering efforts goes into getting microservice type architecture working. We gotta do all those different things that I talked about, right? We gotta figure out how we break down our monolithic application into microservices. We got to containerize that microservice. We got to, orchestrate it across many different servers. We got to add observability. It gets quite complex, so it creates a lot of opportunity in the field. So let's go back to this picture and talk about the scalability and flexibility of teams. And there's a couple different points here. So since your application is broken down into smaller components, not only do you have the flexibility to use different code and libraries, but you can also have smaller teams. And smaller engineering teams are a lot more efficient in DevOps and development, almost in anything, actually. You can't just throw more workers and expect a project to finish faster, right? At a certain point, you get diminishing returns that almost get to zero, where you add another engineer, you're not going any faster, right? If you have 100 engineers and you add 5 more, it's probably not going to speed up the rate that the application is getting developed in a monolithic type application. Whereas if you have teams of just 5 engineers and you add another engineer, it can really help things out, really speed things up. And most large companies are going towards this model, and they follow what's called the 2 pizza rule. So what the 2 pizza rule is, is basically your team should be able to be fed by just like 2 pizzas, right? I guess a large pizza has 8 slices, so that's 16 slices. People eat 2 to 3 slices, so a team should be around 5 people, right? And this is actually a quote from Jeff Bezos, the founder of Amazon. So they try to create teams that are no larger that can be fed by 2 pizzas, and we call it the 2 pizza team rule. So in DevOps and development, we really like small teams, a lot more agile, and it's just a lot more efficient. Yeah, some of us could eat an entire pizza. On some nights I know I could. So microservices in the industry. So hundreds of microservices deployed thousands of times per day. And that's really the main reason we're using microservices. The scalability and everything is awesome, but what these big companies care about is they want to be able to rapidly develop, bring updates as many times per day as they can, right? Companies like Netflix, Amazon, Google, they all do this. I read an article about GitHub, and they're doing thousands of what's called a PR, and basically they're pushing their code thousands of times per day. So there's a lot of automation that you need to build in to actually test your changes and deploy the changes and get them up and running. And a microservice type architecture really allows us to achieve that. So let's talk about the anatomy of a microservice. So in a microservice, there's usually 2 main components that you're concerned about. You have your application logic. This is basically your code, what your application is going to be doing. And then you have some type of data store for your persistent storage, right? And these are things like databases, caches, anything like that. Anything that you can store data, whether it be for long-term, like a database, or short-term, like a cache. Applications usually need to store data at some point, right? And with a microservice, you usually integrate these together. Within the microservice, you should have what's known as a public API, right? So this green part of the microservice, you consider this your sort of like application logic, your sort of backend code on how everything glues together. But this blue portion can be your public API. And what your public API is used for is how the other services talk to your application. So we can see this could be like an Uber type, like an Uber Eats type of application, right? Get restaurants or post restaurants, right? So basically what this is a RESTful API call. And what a RESTful API call is basically it's just an API call through the internet, through HTTP. And you can assume that get restaurants is going to get you a list of restaurants, right? So basically what you want in your microservice is to define a bunch of different public API endpoints. And this /restaurant would be considered an endpoint, but your API could be made up of many, many different endpoints. And this is basically going to be the functionality of your microservice. And once you make those public APIs accessible to your other microservices, then they have access to it, right? So other different microservices, if they called this restaurant API, all they would have to do is send a get restaurants request, and the application code in this microservice would go to the data store, which would be something like an RDS database, pull down the list of restaurants, do whatever type of application logic that it wants to do. It could organize the data, filter the data however it wants. And then in the return call on the API request, it can present the data in whatever format that it wants, right? Usually it's what's known as JSON data. And this is sort of what it would look like when all the different things are talking together, right? I mentioned here that communication is through RESTful APIs, but you can also use things like message queues. We'll get into that a little bit later. But for the most part, these different applications talk to each other directly through their public APIs, right? So you can see the drivers microservice is talking to the restaurant microservice's public API, and it's also talking to the location API, right? So we need to get the location of our drivers, and the drivers need to get the restaurants that they need to go pick up everything from, right? So here you can just sort of see how the application talks to each other and how it works, right? So all these different microservices have their own data store, they have their own application logic, and their own public API. So a little bit more about service meshes. So once you've moved to the design pattern of microservices, the whole different world of possibilities open up. So you can scale up each service independently from each other, and you can decouple the release cycles of each service, right? So let's go back to the other photo here. Just sort of illustrates this a little bit more. So if the restaurant team responsible for the restaurant microservice wanted to make a change, they could make the change on their application code. And as long as they're not affecting the output of their public API, then none of the other applications need to be updated, right? You could update the restaurant application hundreds, thousands of times a day if they wanted, right? Do bug fixes, whatever they want. And none of these other microservices would care. As long as they can call the public API and they have the information they request presented to them in a format that they expect, then everything is going to work in the application. This point here, you're free to write each service in the technology of your choice. We sort of hit on this many different times, but basically, whenever you make a microservice, you can use whatever library or programming language you want, any type of data store that you want, right? None of the other microservices are going to impact your choice for your microservice. And then finally here, you can build and organize your entire organization based on the independent services, right? So going back to this example, you could have a developer team for the restaurant microservice, a developer team for the location microservice, a development team for the ordering microservice, et cetera, right? In reality, from what I've seen, most of the time is larger applications are built up not just of 5 microservices, it can be hundreds. And usually a team is responsible for a certain set of microservices. So I've seen teams responsible for, 3 to 7 microservices. It really depends on the organization. But ideally, single team, single microservice, or they take care of a couple microservices. So we sort of discussed this, but let's hit it in a little more detail. So the monolithic problems that we had are dead, but microservices present their own sort of complications and complexities. So the first one is service discovery. So one thing that needs to happen is these different microservices need to be able to find each other and talk to each other. In Kubernetes, we have service meshes that can implement this for us, but we also have just like basic services, and you can think of them as a load balancer, right? So what a load balancer does, simply put, is basically you have a single box. I should get a paint application. Open here. So how a load balancer works is you have a single box, and then you would have many different microservices, right? And you would send the traffic to the load balancer, and the load balancer distributes the traffic to the microservices, right? And then that way, you only have to know the location of this load balancer right here, and then it sends it out to the actual services. I just installed Windows 11, so they changed the paint application. So sorry for the quality of that little diagram, but I was just trying to illustrate a point. So service discovery, one thing that needs to happen. The next thing is traffic management. So we're going to distribute these microservices across different data sets, different locations, and basically it becomes a little complex of how these different, not only how like these microservices discover each other, but how they route the traffic to each other, right? So there's a little more complexities with like the different routing that needs to happen, everything like that. Security and policies management. Basically, we need to implement security, not just on a single monolithic application, but we need to go into different microservices now and make sure they're secure. We need to make sure that all the different libraries they're using are up to date and they don't have vulnerabilities. We need to make sure that microservices are only accepting connections from other microservices that they expect that should be calling to them, right? Like the payments application only expects certain microservices to talk to the payments app, right? So you need to implement security at the microservice level. Then finally, observability. We sort of discussed this. Since our application is distributed across many different servers, in little tiny microservices, we need a way to monitor that, right? So we need to implement a lot of different observability tools. So let's get into some of the principles, and we will take a break soon, but let's get into, before we do, let's get into the first principle. So the first principle is microservices only rely on each other's public API. So here is an example that illustrates this quite well, right? So I sort of discussed what this diagram is, right? The green part is the application logic. This gray thing here is the data store or database. And then the blue portion is the public API, right? So the way that microservice A should talk to microservice B is it should call the public API of microservice B. If you look at this example below, you can see microservice A is calling the database or the data store of microservice B. And that's not something you want to do. You don't want microservice A talking to microservices B's database. You want all the communication to go through the public API, and that public API is how you control the information the microservice gets, right? This data store or this database should be locked down so only microservice B can talk to it. And if microservice A needs to query this database, it talks to the public API. It cannot talk to the database directly. I see something in chat. If our team is focused on CI/CD for policy and security, will we cross over into cybersecurity from time to time? Yes, you will cross into cybersecurity from time to time. So nowadays, security is everyone's responsibility. And as DevOps engineers, it's especially our responsibility, right? Because not only are we working in the application code and working with the containers, we're working with the servers, we're working with the network, we're working with like AWS and like the cloud platforms. Basically, a DevOps engineer is touching every single different layer. And we need to make sure security is implemented on all those different layers, right? So we're going to do this with like access lists. We're going to do it with API routers and API gateways. But I think what Brandon was asking here was focused around CI/CD. So what I've seen for CI/CD is basically the security team will say, okay, you're allowed to use these container images and only these container images, right? So your security team is going to give you sort of like a list of what you can and cannot do. And then they'll also say, you need to run this scanning tool, right? So basically in the CI/CD pipeline, make sure this scanning tool is run before you release your artifact, before you release your container image or your Java application or whatever it is to the world, right? You need to make sure the scanning application runs and it passes all the tests. So as a DevOps engineer, you're going to be implementing a lot of these different security checkpoints, where the security teams are mostly telling people like what you can and cannot do. And they're running like audit reports and stuff like that. I'm not a big fan of security. DevOps is a lot more fun. So let's finish up principle 1. So principle 1, make sure you talk to the public API. I think I have one more example here. Maybe not. Maybe it's in a future slide. Let's stop here. And when we come back, we will talk about principle number 2. So let's come back at 7 minutes after, and we'll get into principle number 2. Thanks, everyone, and I'll see everyone in at 5:07 my time, which is 7:07 Eastern time or Central time.
All right, thank you.
No problem. All right. So we are back. Let's talk about principle number 2. So we want to use the right tool for the job. And using the right tool for the job is also known as polygot programming and polygot persistence. These are 2 examples of using the right tool for the job, right? So let me read these out for you. Polygot programming is an approach to software development where multiple programming languages are used in a single project. This means that different parts of the software application are written in different programming languages based on the strengths and suitability of each language in the particular task. Now, polygot persistence is the same thing, but we're using that for our data stores, right? So polygot persistence is an approach to data storage where different types of data are stored using different database technologies instead of relying on a single one-size-fits-all database solution. So for example, if you have structured data, then you would use something like a SQL database. If you had unstructured database, then you would use something like DocumentDB, right? So our different data has different requirements. We want to make sure we use the correct solution for that rather than getting, we use this database at this company and we don't look at any other solutions. We don't want that, right? We want freedom to choose the best programming language and the best persistence storage for our actual microservice, right? So that's principle number 2. Don't just use whatever's out there. Use the right tool for solving the problem that microservice is actually trying to solve. The next principle is to secure your service. So, as I mentioned, security is implemented at every single layer of, the infrastructure of the application, right? Security, your security practice should be what's an onion, right? There should be many different layers of your security methodology, right? So back in the old days, we used to just have a firewall and we would set up that firewall and that was our security, right? Nowadays, we secure every single different component that we can secure it, right? So we do defense in depth. So when you get into like the AWS portion, they'll talk about setting up things like VPCs, and then security groups and setting up TLS and encryption, all those different things. You'll need to implement security at the actual server and the container level, as well as the application level. And then you can use things like, sorry for the sirens, you can use things like IAM policies. Basically what an IAM policy is it's a role that you can give your servers and your users in Amazon. And basically it's the permissions that those users can perform. And the IAM role can be assigned to your servers as well, not just people. So yeah, network level, server, container level, application level, also the gateway, which is the front door to your application. So this is going to be your basic firewalls. Sorry, I'm just going to wait for these sirens to stop. They're right outside my window. Sorry about that. I live in the city. It does not happen that frequently, but that was, I guess a fire truck was stuck or something. He was not happy with what was going on outside. So let's continue where I left off. So the gateway, the front door, right? Your firewalls, you're going to have security there. One common place that you're going to be hitting a lot as a DevOps engineer, and what's really important nowadays for these like microservice type architecture, these distributed applications, is API throttling. And oh, I skipped ahead, but one solution for this is an API gateway that Cloudflare gives you. And I'm just going to send this to the chat. This is just like a marketing thing for Cloudflare, but it tells you exactly what an API gateway is and what it does. But basically, an API gateway is what's known as like a layer 7 firewall. And basically what it can do is it can look at all the requests that are coming into your website, and it can scan them and it can look at them, and then it can throttle them, right? So throttling might happen if a user kept sending requests to an API endpoint, right? So the API gateway would be like, whoa, you just sent me 100,000 requests in a minute when an average user sends 10. You're done, you're banned. So that's like what an API gateway can do. And this is really important because there's hackers out there, not even hackers, just like script kiddies. And they'll basically, whenever they find an IP address or a website, a URL, they're going to scan all the endpoints, and they're going to go /admin / blah, blah, blah. And they're going to try to look for vulnerabilities in your application. And something like an API gateway can prevent that, right? It can throttle the amount of requests. It can, it has known IPs that it bans, all these different protections an API gateway can provide, right? So that's just one of the many different things that you can use, and Cloudflare is really good for that. The next thing is authentication and authorization. So obviously, you're going to want to authenticate requests. If you ever worked with an open API on the internet, they probably give you what's known as API token. So if you're trying to use the ChatGPT API, you can't talk to the API without an API token, right? And API tokens just allow you to know, hey, this request is coming from this user, and if they're doing anything bad, we're going to ban the token, right? And then the token's associated with like an email address, and getting a token is not easy, right? You can't just make up tokens, you need to get them. So you should be implementing things like API tokens and just doing authentication. And then finally, things like secret management. You should have secrets and encryption on those secrets and everything like that. So tons of security that you should be thinking about whenever you're creating a microservice style application. The next one is be a good citizen within the ecosystem. So just looking at this example, so basically service A talking to service B, Sally talking to Paul. So Sally tells Paul, hey, I need to fetch certain restaurant details from your application, right? And then Paul responds, oh, okay, which actual APIs are you interested in? Let me know your use cases and I'll provide you the details, as well as I'll register your service as a client, right? Paul is implementing security. By default, Paul probably has his microservice denying all requests to his API. And then once Sally confirms that she wants to talk to it, then he'll add access to her microservice to actually call it, right? So he'll probably give her an API token, something like that. Also, being a good citizen comes down to monitoring and tracing. So in IT, we have a thing called service level agreement, also known as SLA. So you should be providing some sort of SLA or SLO, service level objective, basically saying, hey, our API is available 99.999% of the time, it's online. Here's a dashboard that says that it's available this amount of time, right? So you have your microservice, you create a dashboard showing that it's always available, and you show that to the world like, hey, our microservice is really good. It's always available. Also, just be aware of your downstream dependencies. Let's move on to these other 3 points, though. So you can talk about shared metrics, request time, time to first byte. You just add these into your dashboard. And basically what this slide is talking about is you want to make it so your microservice is giving all the different metrics available that it can give and publishing them. So things like your Prometheus scraper can scrape them and you can have them in a dashboard. And basically, yeah, just being able to do that, making sure the logging is set to a certain standard and it sort of adopts what other people are doing in your organization, then yeah, that's just being a good person, right? So let's talk about how we can actually move from a monolithic architecture to a microservice architecture. So moving from a monolithic architecture to a microservice architecture is not an easy task, but it's something most companies strive to do. The next set of slides is to go over the best practices on how teams can evolve their monolith to microservices. Also, we don't always come from a monolith. Sometimes we start fresh, and doing these different things is going to allow you to, start fresh and develop a microservice type application. So let's talk about some of the different considerations that you need to think about when you're developing your microservice application. So the first thing is we want to decompose the monolith. And basically all this means is we take a look at our big monolithic application, and then we just decide what should be the different components of that monolith and like how we break out those different components, right? And we usually do this by breaking out the business capability and sort of like the business logic. So it gives some examples here. So you could have the product catalog management, the inventory management, order management, delivery management. Basically, this application just has all the different components and breaks them down separately. So once you identified all the different business capabilities, the required services can be built corresponding to each of those identified business capabilities. Each of these different components can be owned by different teams, as we discuss, and those different teams can be experts within that domain. And then you can also use the different technologies that best suit that actual service, right? So the Polygot programming and the Polygot persistence, use the right tools to develop those services. And doing this usually leads to more stable API boundaries and more stable teams and a more stable application. Once you have your monolithic application decomposed into different components, it's a time to actually build and deploy those components. So For example, you can choose to build a user service in Java with MySQL database and a product recommendation service with something like Scala and Spark. Once you've developed your microservice, you can use CI/CD pipelines, and you can set them up using whatever CI service you want, like Jenkins, Circle CI, GitHub Actions, and it can run the automated test against those individual microservices, right? And since things aren't coupled together, those tests, they don't impact each other. Now, when it comes to design, you need to design the individual services carefully. When designing the services, carefully define them and think about what will be exposed and which protocol should be used to interact with the services. It's also very important to hide any complexity and implementation details of the service and only expose what is needed to the service clients. So I want to hit on this point. Basically, what this is saying is you keep your application logic hidden, you keep your data store hidden, and you're just presenting your public API. And then you provide the documentation or whatever is needed to the downstream services on how to call your public API and what information that public API is going to give the microservices. So you want to hide all the complexities and basically just say, call this API and you're going to get this information. Call our restaurants list API and it's going to give you a list of restaurants. Call our drivers API and it's going to give you a list of all the available drivers. Something simple like that. You want to keep it very simple. If any of the unnecessary details are exposed, it becomes very difficult to change the service later, as it'll be a lot of painstaking work for people that are relying on it. So to hit on this a little bit more, basically you want to, whenever you create a service and something else is calling that service, you now have a dependency, right? If you make changes on this service, it's going to impact this service because it's calling it. Now, since you're only making the changes, they're only calling the public API. It doesn't matter if you change the application logic, as long as the data that the public API is presenting is the same and it's consistent, it doesn't matter. Let's talk about a bad practice when it comes to two services sharing the same database in this example. So in this diagram, we have service 1 and we have service 2. And service 1 owns the database, but for some reason, service 2 is calling the database. And this is not a rare scenario, right? Service 1 has like the restaurants database and it has a list of all the restaurants. And then maybe service 2 wants to look at that data and be like, oh, I need a list of the restaurants. Instead of calling service 1, what it's doing is it's just reading the database. And, service 2 goes, oh, well, I understand databases. Oh, you have this table called restaurants. And, you have this field called name and then another field called location. Oh, okay, I'll just read your database and then build my application off that. Now that presents a problem because if service 1 wants to change the schema of the database, service 2 is no longer going to work because service 2 is expecting the database schema to be in a certain format when they wrote that code, right? So this presents a big problem that should not be there, right? You don't want service 2 talking to that database directly. You want it talking to service 1. So this is the preferred approach, right? Service 2 talks to service 1 and says, hey, give me a list of restaurants. Service 1 talks to the database. Then service 1 returns the list of restaurants to service 2. Now, when you go to make a change to the database, you only need to change the application code in service 1, right? Service 2 doesn't care that the database schema changed at all. It also presents, or it also prevents two different problems that you may run into. If you had two services talking to the same database and writing to it, that can create a lot of problems with write locks, but you can also run into performance problems, right? So say service 2 wants to talk to this database. It could make a very inefficient query to the database, something like select star from all tables, right? And that's a very inefficient query, and it could really slow down the database, right? Because there's hundreds of thousands of restaurants in this database, maybe. And every time the service wants to get a list of it, it's just saying, give me all the restaurants, give me all the restaurants. They haven't optimized their query or anything. So that's going to impact service 1's database. And, this team is going to be like, why is our database so slow, right? So doing it this way, service 1 is the only one that talks to the database. They're going to be the only one that is actually slowing down this database, and it just makes that component ownership a lot tighter. Let's talk about how we can decentralize things. So with microservices, we're trying to decentralize everything, right? We don't have that single monolith. And one way we can achieve this is through message bus. So I talked about the one way that microservices can talk to each other, which is through API calls, through a REST API call. But another way is you can drop a message into what's called a message bus, right? And all this is basically a message queue. And there's many different types of message queues and queuing strategies, but the simplest one that I can bring up here is just like a simple message queue, first in, first out, right? So basically you send a message to this queue. You have writers and consumers. So your writers are going to write messages to your queue, and then your consumers are going to read messages from that queue, right? So service 1 might be a writer, and it's going to write messages to the queue. And then service 4 could be a consumer of that queue and goes, oh, okay, I see this message. Now I'm going to do some work. So an example application that I can come up with here is, if you've ever been on the internet and you've looked for one of those converter sites where you go, okay, I have this file format. Can you convert it to this format, right? Can you convert my MP3 to a .wav file, right? So service 1 might be the actual website that you go to, and it's talking to the user. And basically the user goes, okay, I'm going to upload the file, right? And service 1 uploads the file, stores it onto some data store, and then it sends a message to the message queue and says, okay, I have a file at this location that's in the MP3 format, and I want it converted to .wav. So it'll send it to the message bus, and then service 4 could be our converter service. And then service 4 will go, okay, there's a new message in the queue. The message says this file name, and it wants to convert MP3 to .wav. Okay, I'm going to convert it. And then once it's done, it sends the done message saying the file is now ready. And then service 1 can pick it up. Okay, that job is done. The completed file in the .wav format is here. Go pick it up, right? So that is an example of how you can use a message queue, right? I hope I didn't overcomplicate the scenario too much, but basically it's just a way you send a message to this queue, And then other different services can pick up the message, and then they can do work based on that message. So let's hit off some of the key points here. So the bus handles the routing of messages from different services. Message brokers like RabbitMQ are a good example, right? So RabbitMQ is a message broker, but it also has a lot of different message buses. RabbitMQ is just a way of managing many different message buses, and it can route messages from your different services to your message bus. Realistically, as DevOps engineers, we don't care too much about the logic of how these messages get in here. But one of the things that we do is we create these queues. And it's actually really simple to do if you're using something like Amazon. You basically go into Amazon, you click a few different drop downs, you select the name of the queue, and then you create the queue, right? And then it's really up to the developers to use that queue. So I don't want to overcomplicate the logic of when you use these message buses or these message queues, as a lot of us here will just be responsible for actually creating them. And, they're very simple to create in the cloud platforms. But let's hit on the rest of the key points before I leave this slide. So a couple different problems happen when developers start using these queues. Sometimes they build too much logic within the routing systems of these queues, when it should really just be a message saying, hey, I need some work done. This is what you need to know about the work, right? So our MP3 to WAV example, basically it says, I need you to convert this file to this file format to this file format, and the file is located here, right? That's as much logic as our application would need, right? So you should just keep it as that. Where people run into trouble is they say, oh, do this, if that, then do this, right? They add a bunch of logic, and you really shouldn't be having any logic in your message buses, right? So best practice is to dumb it down and keep it simple. Now, this one is important when you're working on a team. So when there are multiple teams taking care of different services independently, it's best to introduce some sort of standards, best practices, and documentation, right? So a single organization with many different teams working on many different microservices, although they can have their own sort of like code bases, and this team uses Python, this team uses Java, this team uses Go, this team uses Rust, there should be some sort of standardization, right? Okay, for logging, we use this type of format of logging, right? We say logging messages, right? For logging the details of our application in messages. Maybe you have, okay, the format should be the date, the severity, error, warning, debug, whatever. So date, severity, and then the actual message, right? So that's the kind of standards that you want to follow, right? Maybe you say, okay, every single microservice needs to provide how much CPU usage they're using, how much memory usage they're using, how much latency the user is experiencing when that API is called, right? So certain standards and best practices should be used throughout the organization. Now, the really important one is documentation, right? These standards and best practices don't always get followed, but documentation really, really needs to be followed. And there's tools like Swagger that help us automatically document our APIs as we build them. Basically, we have our application, we can use something like Swagger, it reads our application code, and it builds documentation for us. And the documentation will look something like this example here. So I'm just going to open it up. And this is PayPal's documentation for using their API, right? So basically every single API out there should have documentation that sort of looks like this, that goes over everything that a developer would need to know to program something to talk to this API, right? So if you search for any API, you should be able to find documentation that looks like this. So this is PayPal's example, and you can see here, it sort of gives you an introduction, what type of account you need, the different account types. Then it talks about authentication. So if we just go through this, okay, so if we want to send a post request, we need to provide a token that has a client ID and a client secret. And we need to specify this header. And then we need to specify grant type of client credentials, right? So it tells you how to do that. And it says, hey, you're going to have to change client ID and client secret to your actual tokens that we give you, right, in your account. So you'd have to log into the dashboard, sign up, get these client ID and client secrets, and then have that in all your different payloads. Then gives you some examples, and then it gives you a sample response, right? So if you were to talk to the PayPal API, this is what a simple example response would look like. Then it goes into all the different resources, right? So I haven't really looked through all this yet, but let's go. So let's take a look at orders. Buttons aren't working. I wonder if my ad blocker is causing issues. Okay, we will look at this one. So shipment tracking, right? So reading these API documentation sort of give you a better idea of how these APIs actually work, right? So adding tracking information for multiple PayPal transactions, it sort of gives you what the API is all about, right? So if you want to update tracking details, show tracking information, or cancel tracking numbers, right? So I guess this is if you were to send something to someone and a PayPal shipment where they pay using PayPal, they could track your shipment using these endpoints, right? And you could develop your own little Android application that calls this shipment tracking API, right? And you would call it just by posting this message, v1 shipping trackers batch, and you would set the parameters like this, right? So this is what all the documentation sort of looks like. And you can see the responses. I actually have a really good video about this on YouTube that goes over the coin market cap API. So if anyone's interested in that, I go into much better detail on that. But as DevOps, we don't really work with the APIs too much. This is more about what the developers are doing and how they're creating these APIs, right? So don't worry too much about understanding all these different like post and get requests and how these different applications talk to each other, right? So monitoring and logging. So microservice architectures, we want to implement a lot of different monitoring and logging. And this is because it's distributed across lots of different servers, and we need to know what's going on, right? So if your application's having issues and someone says the user is on Twitter and he's like, hey, this application isn't working, what's going on? Like, what do you do? There's not like a single server that you can log in, right? Back in the older days, the monolithic application was running on the single server. And if the users were saying the application isn't working, you just log into the server and you look at the logs on that server and you can figure things out. That's not what it's like nowadays. Now, basically, we have our dashboards, and usually we can even figure out if there's a problem before the user even reports it, right? Because we can set triggers on alarms like CPU and anything like that. And we can usually detect the problem before it even happens, especially if we have our observability tools tuned properly. So there's two main things that you sort of need to think about when it comes to monitoring microservices. And that's the log aggregation. And then there's the metrics and stat aggregation. So the logs aggregation. So if you're familiar with troubleshooting any type of application, you're probably familiar with getting like a log file, right? And these log files contain basically everything the application was trying to do, right? So when the application starts, it probably says, application is starting, application is running this process, application blah, 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 application started on this IP address, running this endpoints, right? Any information about how the application is running is going to be in these log files. So we have lots of different tools to ship those log files into other observability tools. This example talks about the ELK stack, which is Elasticsearch, Logstash, and Kibana. Basically, this is just a tool that you can log into, and all your different servers and microservices are going to send logs to it. And then you can log on to this one place and see all your different logs. So that's what log aggregation is. The next thing is metrics and stats aggregation. So your metrics are things like how much CPU you're using, how much memory you're using, and how long it took the user to log in, right? When you log into Netflix, there's going to be a stat saying user took 3 seconds to log in. User took 1 second to log in, right? And Netflix is going to be graphing this, and they're going to be like, oh, X amount of users are taking 10 seconds to log in. There must be a problem with the login microservice or something with the network talking to the login microservice, right? So basically anything you can think of in regards to the application performance and the actual like architecture or infrastructure, you can get metrics for that, you can get stats for that, and you want to aggregate that, send it off into a system where you can build dashboards. So we need to make sure that our applications are set up so our dashboards can take in those metrics and logs. So I'm just going to have a drink here. Sorry, losing my voice a little bit, but we're at the end here. We have a quiz that I'll go over, but before I go over it, I just want to ask if there's any questions so far. Okay, it doesn't look like it. So let's go over the quiz, and you can speak up or just answer in chat what you think the answer is. And then once we're done that, we'll be done for the day. So let's go over this. So question 1, fill in the blank. A monolithic application is built as a single unit, built to handle functionality and data of many applications, both or none. And everyone is saying A, and everyone C, built to handle functionality. It's A. I can sort of see why you might say C. but A is the answer here. I think the answer isn't really worded that nicely for B. Maybe it should say, they're trying to say that that's a microservice. Question 2. Single point failure example is monolithic, microservice, both the above, none the above.
A. Monolith.
So we got an A. I think got 2 A's. Yeah, monolithic. So I see Idris said A and then changed to C, or he said C for this one. Microservices, sorry, let's go back. Microservices can have a single point of failure, but for the most part, they are compartmentalized. Monoliths are for sure a single point of failure, right? If any part of the monolithic application stops working, the whole application crashes. With microservices, if a single microservice crashes, most likely the rest of the application is okay, right? But there's certain like microservices that lots of different microservices talk to, and it can sort of become a single point of failure. So I would say A is the more correct answer, but C does sort of make sense as well. So agile development and deployment is difficult in the case of monolithic, microservice, both, or none.
That's a D.
D. So I believe the answer is A. But I would actually say A or C, because agile development is difficult in every case, in my opinion. Agile never seems to work. But the correct answer, we'll say, is A. Monolithic sort of follows what we call waterfall, right? Basically, waterfall means you plan out all your changes. You go, okay, in 3 months from now, we're going to have version 2 of our application, and it's going to have these hundreds of different changes, right? Whereas agile, like every week, every 2 weeks, you sort of have a sprint and you're trying to get all your different updates. And with microservices, you can update them, individually. So question 4, complexity of developing, testing, and deploying distributed systems and handling partial failures account to the disadvantage of. So basically, this question is saying,
A. Yeah.
So this question is saying the complexity of developing and testing and deploying a distributed system is a disadvantage, right? So distributed sort of means like microservice, right? Yeah. So microservices. It was sort of a trick question. But yeah, anytime you see like distributed, think microservices, right? Because microservices are small and they're distributed across like many, many different servers and components. So software built as microservices can by definition be broken down into multiple component services.
True.
True, right? Microservices are just applications that we have broken down. So that is the quiz, and that is it for the class today on microservices. I know it was a lot of lecture. I know everything was sort of like pie in the sky, like concepts and everything. But I think it sort of lays down the foundation of what we're going to get into, which is going to be Docker and containerization and Kubernetes. And the stuff coming up is a lot more exciting, in my opinion. And we're actually going to, deploy microservices. I see Kobe has a question, so go ahead, Kobe.
It's actually a correction, if I may. Agile is not difficult. It's the people who do agile that can be difficult.
It's true. It's true. And people can tend to be very difficult, especially in the development world. And yeah, certain developers, I find every developer has their own way.
Yeah.
Yeah. All right. So if there's no questions, I will let everyone go for the night.
Thank you very much, Brad. See
Thank
you.
you. Thanks, everyone. See ya.
Yeah.